Our last example is the maximum cut problem. Um, the definition of maximum cut is the following. Say, given an undirected graph with positive integer edge weights. So all the weights are integers and they are all positive. Okay? And we're supposed to find the node partition A and B. That is to assign the nodes two different colors, either white or black or red or blue, and so on and so forth, such that the total weight of edges crossing the cut is maximized. Okay, that is to maximize this function. This function is the total weight of all the edges u and v, such that u belongs to one set and v belongs to the other set. That is the total weight of the edges of which the two ends have different colors. So it's like this. To understand this problem, let's think about, say, attending a conference with n talks. So each talk corresponds to a node in this graph. All right, and the edge corresponds to people. If we have one edge between two nodes, it means that this person is interested in both talks. All right, so everyone has a chance to tell the hosts two of their favorite talks. All right, so if we schedule the two talks both in the morning or both in the afternoon, it will be inconvenient to the person who would like to attend both talks, right? So to make everybody happy, we should schedule some of the talks in the morning and some other talks in the afternoon, so everybody can be happy to attend one talk in the morning and the other talk in the afternoon. Okay, so that's the toy application. Say we have n activities and m people, and so each person wants to participate in two of the activities. And we're supposed to schedule each activity in the morning or afternoon to maximize number of people that can enjoy both activities. So we like to make as many people happy as possible. And of course, there are other real applications in circuit layout or statistical physics. Well, the way it's related to local search is the following. First of all, the problem is to maximize this weight function, okay? And the feasible set contains all kinds of partitions. And the neighborhood S prime can be obtained from S by moving one node from A to B, or one from B to A. That is, to flip the color of one node to obtain the S prime from S. So it's called a single flip neighborhood. All right, does it look familiar to you? Isn't it merely a special case of the Hopfield neural network, right? With all the weights being positive. That is, for every edge, we would like to have its two endpoints in different colors, or say in different states, right? To maximize the weight function is the same to say we want to maximize this phi of S, which is the sum of the weights of all the good edges. So we already have a solution, right? That is, we start from an arbitrary configuration. For example, at the very beginning, we assign everyone the same color, right? If this configuration is not stable, we try to find one node that is not satisfied and flip its state. And that's it. So here we have a very simple solution. When it terminates, we're going to end up at a local optimum, but not necessarily a global optimum, of course. And the key problem is, first of all, it may not be in polynomial time. So now researchers are working in mainly three directions. One is to get a polynomial time algorithm. And second is to estimate how good is this local optimum, about measuring the quality of the solution. Okay. And the third one is, in order to get a better solution, one direction is to try a better definition of the local. It means let's try to define the neighborhood in a different way. So hopefully we can get a better result. Then we're going to talk about each direction a little bit. Let's start from the quality of this local optimum. Here's a conclusion about the quality, about the approximation ratio actually. We say that let this one, AB, be a local optimum partition. And let A star, B star be a global optimal partition. That is the real optimal solution we're looking for. This local optimum we obtained from the single flipping algorithm is no less than 1/2 of the real optimum. Which means what? Which means the approximation ratio is about 2, right? Now let's try to prove it. The proof is quite straightforward, so let's go through it. First of all, since this is a local optimum partition, that means for any u in A, this part is the weight of all the bad edges, and this part is the weight of all the good edges, right? And if this is a local optimum, it means that every node is satisfied. So this must be true for all the nodes, at least in A, right? Now let's sum them up. Let's sum them up for all those u's, all right? So we sum up both sides of the inequality. What do we get? For this part, it's the sum of all the weights with u and v are both in A, right? So we sum up the weights for every uv and every vu. So each edge is summed twice, right? And therefore, it can be simplified as 2 times the sum of all the weights for all the edges in A, all right? And how about that part? That part is exactly the definition of this weight of cut, right? So this is just W of A and B. And therefore, we get this inequality for all the nodes in A, right? And similarly, we can prove the same thing for all the nodes in B. And therefore, for all the edges in B, we have the similar inequality. All right, let's sum them up. And what do we get? We have that this one plus this one is certainly less than or equal to 2 times this W, right? Therefore, we can divide both sides by 2, and we get this one plus this one is smaller than or equal to 1W, right? And then let's add 1W to both sides, so we get this inequality. And what is this part? Is the total weight of all the edges, right? It's for all the edges in A and all the edges in B, plus all the edges crossing the 2 sets, right? So what is the relation between this total weight and the global optimum? This W of A star and B star. W of A star and B star is certainly no more than the total weight, right? And therefore, we have just proved that the global optimum is no more than 2 times the local optimum. Or in other words, the local optimum is at least 1/2 of the real optimum. And that completes the proof. So in 1976, it's been proven that there exists a 2 approximation algorithm for this max cut. All right, can we get anything better than this? And the answer is yes. Almost 20 years later, it's been proven that there exists a 1.1382 approximation algorithm for max cut. So what is this? Looks so strange, right? It's actually obtained by this formula, okay? So it's been proven that the upper bound of the approximation ratio is given by this function. And the minimum is approximately 1.1, a little bit more than 1.1, okay? And 2 years later, it's been proven that unless p equals np, there's no way to get a better result than 17/16 approximation algorithm. Okay, so what is this? This is approximately 1.06. So it's a little bit less than 1.1. That is so far the lower bound for the approximation ratio. Unless p equals np, we would not be able to get anything better than this. Okay, now the next subject, on the polynomial time algorithm. According to the analysis we have done before, we know that the single flipping algorithm can stop in w steps, but that w is not polynomial. It's actually exponential, right? And one thought is to stop the algorithm when there are no big enough improvements. Of course, we have to define how big is big enough, right? So here is the big improvement flip algorithm. We only choose a node which, when flipped, increases the cut value by at least that many. That's 2 epsilon over the size of v, or say 2 epsilon over n, times the weight of the cut. So you see that when epsilon tends to 0, this tends to the accurate local solution, right? And we claim that upon termination, the big improvement flip algorithm returns a cut so that the approximation ratio is just a little bit more than 2. It's 2 plus epsilon approximation. And another conclusion is that the big improvement flip algorithm terminates after at most that many flips. So what is this? This is indeed polynomial, right? Because here we have a polynomial of n, a polynomial of 1 over epsilon, and a polynomial about w. This is log w, right? Which is the number of bits that w occupies. So this is linear. Actually, the proof is not too complicated. Let's see. And since each flip will increase the weight by a factor of at least 2 epsilon over n, right? And therefore, after each flip, the total weight will be greater than or equal to 1 plus epsilon over n. Well, actually, it's 2 epsilon over n. But since I write greater than or equal to here, it's okay to just take a smaller value. Okay, so it's 1 plus epsilon over n times this w of a and b. So this is after one flip. After flipping it for n over epsilon times, the total weight will be what? Greater than or equal to this one to the power of n over epsilon, right? And we say that this is greater than or equal to 2. Here we just applied a mass inequality saying that 1 plus 1 over x to the power x is greater than or equal to 2. Okay, provided that x is greater than or equal to 1. So apply this conclusion to our problem. We say let x be n over epsilon. We can certainly take epsilon sufficiently small so that n over epsilon is greater than or equal to 1. So taking epsilon being smaller than n, we can conclude that this is greater than or equal to 2 times the original weight. So in short, we have that for every n over epsilon flips, we can double the weight once, right? And since the total weight is that capital W, obviously we cannot keep flipping forever, right? That is, we cannot keep doubling the weight forever. So we must stop after k steps. And what is that k? Log W, right? That is the maximum number of times that we can double to get to this W. And that's how we obtain the conclusion. Another direction is to define the neighborhood in a different way. They say the neighborhood of a solution should be rich enough that we do not tend to get stuck in bad local optima, which means if the neighborhood is too small, then the probability of hitting the bad local optima will be high, right? So we want it to be rich so that it's unlikely to get a bad luck. On the other hand, the neighborhood of a solution should not be too large, since we want to be able to efficiently search the set of neighbors for possible local moves, right? One direction of making improvement is this. If a single flip is not good enough, let's try to flip k nodes instead of one node each time. Hopefully we can get a neighborhood that contains more possible solutions. So the neighborhood of k flip is much richer than the single flip. Okay, that's one advantage. However, on the other hand, the searching time becomes big theta of n to the power k. That means k cannot be too large. Otherwise, with this kind of complexity, it's still unrealistic to solve the problem. And there's one heuristic algorithm that is between single flip and k flip. It's called KL heuristic. And let's see how it works. So step by step, it will generate a richer neighborhood. Step 1, let's try to make one flip as good as we can. And obviously the time complexity is big O of n, since we just try to flip every node, right? And try to find one that is the best. After this flipping, we obtain one solution, and denoted by a sub 1, b sub 1, plus one node that is marked to be visited. Okay, and before step k, we must have had k minus 1 vertices already marked. Okay, and we make one more flip of an unmarked node as good as we can. Even though it's possible that sometimes there's no way to get a better result, to flip any other node will make the situation worse. Still, we will choose a best one out of those bad cases. Alright, just anyway, let's make one flip of an unmarked node. So as good as we can. We need to check n minus k plus 1 nodes. Alright. And we denote the resulting partition as a sub k, b sub k, and we have k nodes marked. We can keep going like this until step n, where we get a sub n and b sub n that every node has been flipped, and therefore we just obtain the mirror partition. And we define the neighborhood of AB to be the collection of the first n-1 partitions we obtained in the first n-1 steps. And the partition AB is a local optimum if and only if the weight of this cut is greater than or equal to the weight of all those cuts. So overall, it flips at most n times in total, and each flip takes a big O of n times. So altogether, it's only big O of n squared, better than this n to the power k. And this method is actually quite powerful in practice. However, the analysis of its properties is still an open problem. So to summarize, we say that local search is a very general technique in the sense that it's quite easy to design a local search method to solve any hard problem. But on the other hand, it's often used as a kind of heuristic because it's quite difficult to measure the quality of the solution.